Okay, so for this homework problem, we're going to do a finite element analysis of a plate with a hole. It's kind of a common thing to do, and we're going to look at the stress concentration factor. We'll explain some of these terms here in just a few moments. In addition to that, we're going to learn about how to exploit symmetry in our loading, our boundary conditions, and our geometry of our mesh to simplify our problem and make it a little bit smaller problem. So what we'll do is I want everybody to do this same geometry. I'll show you what I want you to vary in just a few minutes, but we're going to take a look at a plate that's got a hole in it. We're going to apply a uniaxial stress remotely from the hole, and we're going to look at what's called the stress concentration factor. Now you may know from another class or mechanics materials or theory of elasticity that if we have a stress concentration, a hole is an example of one, that the stresses near the hole will be higher than the stress away from the hole. And the ratio of that is called the stress concentration factor. Now for our particular geometry, we're going to use a plate that is 200 millimeters wide. We're going to use our SI system this time. 200 millimeters tall. This will be kind of a square. And let's use the radius, not the diameter, the radius of the hole equal to 20 millimeters. Now if we look at this, there are two planes of symmetry to this problem, assuming that the material is symmetric. We have seen that our load is symmetric. But those two planes of symmetry I can sketch in. Let me use a different color. One plane goes vertically. One line right here of symmetry is vertical. And the other line of symmetry is horizontal. Now what this helps us with is we don't have to model this entire structure. All we have to do is model 1/4 of this structure because it's got two planes of symmetry. We can get by with just a quarter symmetric model. So what we are going to model then is going to be this quadrant over here, this first quadrant. It's a little bit rough of a sketch, but I'm trying to draw this quadrant right here. We have our remotely applied stress. Let's call this sigma applied. And that would make the coordinates, let's just go ahead and put these in. 20, 0, 100, 0, 100, 100. Oops. And 0, 100, and 0, 20. So these are key coordinates. We're going to want to map this out when we get ready to do our construct our geometry for this finite element analysis. Now these are all, like I said, in units of millimeters. Now we need to think a little bit about the boundary conditions at this point as well. If we were to pull on this plate in the vertical direction, as I have up here, and down on the bottom, going down that way, then right on this horizontal line of symmetry, there should be no displacement in the vertical direction. Okay, sometimes these symmetry boundary conditions are a little bit tricky to see at first, but once you get the hang of it, it's pretty easy. There's going to be no displacement in the vertical direction on this horizontal line. However, there can be movement in the what I would call the x direction. Let's put our coordinate system right here. Okay, so schematically, the way I'm going to show this boundary condition on the sketch is with rollers that are on this surface. And these rollers are such that they keep the motion constrained in the vertical direction, but they do allow for movement in the x direction. The reason why we need movement in the x direction, as we saw from our first homework problem, we can have a Poisson type contraction, and that same sort of thing happens in this plate. By the same reasoning is that there's no vertical displacement on this line of symmetry, there will also be no vertical no horizontal displacement on the vertical line of symmetry. So also on this edge, we can schematically represent the boundary condition as a set of rollers on these points. So that's what we're going to do. We're going to construct a mesh, a part in Abacus CAE. We're going to apply loads and boundary conditions that match this type of condition. There's one other thing that we need to settle on before we go too much further. We're going to use a plate thickness of 1 millimeter. You can use something different if you want, but for our purposes right now, let's just use 1 millimeter. We're going to have a plane stress type of loading condition. Now before we move into the CAE part, let's talk more about stress concentrations of infinite and finite width plates. There's a famous result from the theory of elasticity that says a small hole in a very large or infinite plate should have a stress concentration factor of 3. If we have a finite width plate, then we're going to get something a little bit different than 3. So let's talk about stress concentrations. The way they're often represented is with a symbol called KT, a theoretical elastic stress concentration factor, and that's defined as a maximum stress in the structure. We just put the subscript whole right here, divided by something that we call a nominal stress. Some people use different symbols for nominal, but what a nominal stress means is nominal means in name only. So this is something that we call a nominal stress. It's a reference stress for our particular geometry. If we have an infinite plate, the applied stress is usually taken as the reference stress. But we're not going to model this as an infinite plate. We're going to model this as a finite width plate. So we need to decide what we're going to use for our nominal stress. And what I want you to do is I want you to use a particular stress concentration factor chart that was derived a long time ago based on some theory of elasticity solutions, and I think there might even be some experimental photoelastic results that were included in it. But I'm going to show you the stress concentration factor chart, and we're going to see what they use as a nominal stress. Right. Let me call that up. Okay, so here's a chart that I'm going to provide to you. This is a chart out of Shigley's machine design book. And on the left axis is the stress concentration factor KT. And on the horizontal axis is a ratio of D over W. And these terms are defined in this figure. The stress concentration factor chart has to define all these kind of terms. But D is the diameter of the hole, and W is the width of the plate. Now I made these kind of small over here, but in our case, our diameter is 40 millimeters. And the width of our plate, W, is 200 millimeters. So down on this is the D over W. So let's go ahead and calculate that. 40 divided by 200. Make sure I don't make any mistake here, just writing it down. That looks like 0.2. Okay, so we're going to go to 0.2 on this axis and take this line up to the curve that we have, and then bring it over and read off the value of the stress concentration factor. Now to me it looks like it's right about in the middle between 2.4 and 2.6, so I'm going to say that this has a stress concentration factor of 2.5. So when we do our finite element analysis, we're going to compare what we get to this stress concentration factor of 2.5. And I don't think I'll give it much away at this point, but we probably aren't going to get 2.5 when we calculate our first stress concentration factor. In homework 3, we're going to talk about something called convergence analysis, and which will try to zone in on the right answer. All right, so we have a stress concentration factor 2.5, and in this particular problem, they say that the nominal stress, they call it sigma naught. It's down here, where the area is defined as W minus D times T, where T is the thickness. So it's the thickness of the plate times the dimension from the edge to the edge of the hole, from the edge of the hole to the edge of the plate. Okay, so that's what they define their nominal stress. Now we want to do something that'll probably make more sense a little bit later. We want to put an applied load on this plate, an applied remote stress on this plate, such that we get 1 megapascal of stress for our nominal stress. So let's write that down. So how much applied stress do we need? Well, I know that if I take and I wanted to calculate my applied stress, if I knew the force in the area, that would be equal to the force divided by the top edge of the plate times the thickness. So the force that's being applied in that structure is the applied stress. I'm going to abbreviate this as sigma amp times 200, and let's just use the symbol T instead of putting in the 1 millimeter. Well, the nominal stress is going to be this force divided by the area that's defined in this term right here. It's the width of the plate minus the diameter of the hole. Now remember, the diameter is 40 millimeters, and then times the thickness of the plate. So it's kind of interesting. The thickness of the plate will go away for both of these terms. And if we want to solve for the applied stress, that will be equal to the nominal stress times 200 minus 40 over 200. Let's see what that is. That's 0.8. Right, so the applied stress is going to be a little bit lower than our nominal stress. And we said we want to have a nominal stress equal to 1 megapascal. So we're going to have an applied stress of 0.8 megapascals. So we're going to keep that in mind as we set up this analysis. All right, so now that we have all this in place, let's save this page, and then I'm going to call up Abacus. All right, so here I am. I have a fresh session that I just called up. And it starts out with an empty model. We're going to do the meshing right here in Abacus instead of importing a mesh like we did last time. And here we have the module list, and it's a drop down that goes through here. Now, the kind of the handy thing about how they have this organized is we're going to proceed pretty much in order of this list from top to the bottom. We're going to start by creating a part. And over here on the top it says create a part. We're going to click on that. The name of that says part 1. Let's just call it plate with hole. It's going to be a 2D planar, deformable, shell feature. In approximate size, it says 200. We'll see later that we want to get a little bit bigger than the size of our component, so I'm just going to put in 400. And our dimensions for our units are going to be millimeters. So we're going to use the Newton and millimeter system, where our units of stress are going to be newtons per square millimeter, which is a megapascal. Okay, we'll click OK. And see, now we have this grid. This is the origin of the system, and we're going to key in some points. So there's all kinds of different lines you can create and tools. We're going to keep it kind of simple. We're just going to hit this first one, create an isolated point, and we're going to punch in those points that we had defined on the previous page. So our first one was 20, 0. That's the edge of the hole. You see it shows up here and with a little pink plus sign. 100, 0. 100, 100. Okay, now when I hit enter, it created a point, but it's outside the viewing area. So I'm going to fit the window, and we'll get a little better look at it. Some of these toolbars end up dropping down. Let's see if I can make my working area a little bit bigger. Okay. And this probably doesn't need to be so big right now. All right. And then we get this corner. I'm going to put in 0, 100 and 0, 20. The next thing I'm going to do is I'm going to connect these with lines, and that's what this says, create lines that are connected. So I'm going to go and just click on these. It kind of snaps to it. You want to do this in the same sense of rotation. So I went around these in a counterclockwise fashion. You can either go clockwise or you can go counterclockwise, but you want to do it in the same consistent way. Next thing we want to do, well, it's still trying to create another line. I'm going to hit escape. That'll get rid of that. And we're going to create an arc. And I don't know if you can see it very well, but this says the little arc symbol has a 1, a 2, and a 3 in it. And that's the order of identifying the points. Number 1 is the center of the arc. Number 2 is the top of the arc. Number 3 is going to be the bottom of the arc. So I'm going to click that and then get that point, that one, and let's try this one. Whoop. And actually I made a circle and not an arc. So I'm going to select it and delete it. I clicked on the wrong symbol there. Okay, so to get rid of it, let's try this eraser. Let's see if this works. It's kind of changed color, and now it's highlighted, and then I'm going to hit done, and it's going to get rid of it. So if you make a mistake, you can recover. All right, let me do the arc now. Here I am at my origin. Here's my top point, and here's my other point. So now I have this nice quarter circular arc. Okay. So we're in good shape now. I'm going to X out of this arc tool. And since we're done sketching our component, we're going to hit done, and it'll get us ready for the next step. So here you can see that it's this kind of gray looking quarter symmetric part of our plate. Now there's all kinds of things you can do with this part module. You can make extrusions and holes and things and whatnot. This is all we need to do for our purposes. Next one down, we're going to go to properties. We're going to create a material, and we'll use material properties for steel again. We're just going to do elastic. And here we have to be a little bit careful again. The modulus of elasticity of steel is about 210 gigapascals, but we need to enter our units in terms of our Newton per square millimeter, which is a megapascal. So for our steel modulus of elasticity, we're going to use 210,000 megapascals, and then our Poisson's ratio is a unitless quantity. We'll just use 0.3 again. We'll use isotropic materials. Take all the defaults for this. So we've created a material. The next thing we need to do is this next one, create a section. This will be a solid type material, homogeneous. So we'll hit continue. We can change the name if we want, but the default is fine. And the material that we're going to use is steel. And now we do want to check this. We're going to use a plane stress type situation, so it's fairly thin in comparison to the other dimensions. And we said we wanted a 1 millimeter thickness, so we're just going to leave this as 1. Okay, so now we've created the section. We have to assign the section. It says select the regions to be assigned. I just move it over here. See it kind of highlighted orange. And I click on it and I hit done. Okay, what section should it be? Section 1, the one that we just created, that's fine. And we're going to hit OK. All right. The next one down is called the assembly. So you can create multiple parts, and the assembly is where you do what's called instancing a part. It's taken me a while. I was kind of uncomfortable with this when CAE first came out. But what this represents is, say you have a bolt that you created a part for, just like we did, but you have 15 bolts in your assembly. You only have to make one bolt, but you can put it in the assembly 15 times. Now for us, we just have the one part that we're going to deal with. So we're going to create an instance, and we're going to create an instance from a part. Now we could create an instance from a model, and a model means some other finite element mesh or something like that. So the part is going to be this one from here. And we have a choice of doing what's called a dependent or an independent type of instance. Let me try to explain what that means. This is another one of these things that seems kind of confusing to me, but I think I got the hang of it now. A dependent part instance means that if we have 15 bolts or 15 plates like this in our assembly, if I go back and I change the mesh on the original part, the mesh will be updated for all the different instances. Right? Now, the independent part will be meshed on the instance. So if I have 15 bolts, I can mesh each one of those 15 bolts differently with a different mesh. For us, we're just going to try a dependent mesh. Let's see if we can get this to work. And in case you had 15 bolts or whatever you have, you can do an auto offset from other instances. You can move them around later on. We're just going to hit apply, and we'll be all right. Have to select the part. So that was highlighted, but let's just hit OK. All right. So we should now have that instanced. Next thing we'll do is we'll get into our steps. Kind of like we did with our first homework problem. Let's take a look at our steps. Oop, I actually ended up with 2 instances. I thought maybe that might have happened. I think I hit apply and then OK, and that made 2 instances. So let's just get rid of this one. We're just going to delete this. We can suppress it, but let's right click on the instances. There should be a manager. Let's see. How about we do this? We'll just suppress. Oh, here it is, delete. We'll just delete this second instance. Okay. All right. We want to get back on track. So we have this initial step, and we're going to put some boundary conditions in the initial step. We're going to put our loads in our first step. So we're going to go down here to the step, and we're going to create a step. It'll be step 1. We're going to do a static general analysis. We'll hit continue. Time period of 1 is fine. Nonlinear geometry off is fine. We'll take all the defaults on this like we did last time. Interaction, we don't have any interactions in this. Like I said, it's if you have 2 things touching each other or making contact, that would be an interaction. So we're going to skip down to the load, and really it's loads and boundary conditions. So we're going to go into the initial, okay, and we're going to right click and we're going to create a displacement boundary condition. We'll call it BC1. That's fine. Hit continue, and it says select the region. So we're going to start with this bottom line. Now you have to be a little bit careful when you select these things. Sometimes it will over select, but I just want that bottom line from the hole to the edge of the plate, and I'm going to click on it, and it's turned red, so I'm going to hit done. And remember, this was the one where we wanted the displacement in the vertical direction to be 0. That's U2. So I'm going to select that and hit OK. But that's not the only boundary condition I need. I'm going to create another one, call it boundary condition 2, on the left edge, on the symmetry line. I want the x displacement to be 0. So now we have those boundary conditions. And these boundary conditions are based on the part. Now if we remesh our part, it will know that we want that boundary condition applied to all the nodes on that edge, as long as we have meshed on the part instance, a dependent instance. Okay, so let's go into step 1. We're going to right click on loads. We're going to create a load. We're going to do a pressure, kind of like we did last time. We're going to select the top line and hit done. And okay, now here's where we said we wanted 0.8 megapascals. I kind of like to work this problem as if it's in tension, and so to make it positive, the arrow's pointing out, I'm going to put minus 0.8, and a ramp amplitude profile is fine. Let's resize it so we can see our arrows. Well, I guess we're going to have to use this tool here. But see, these arrows are pointing out of the top surface of the plate. All right, let's see what's after load. After load is mesh. Okay, so we're going to use an auto meshing feature that's in Abacus. In general, auto meshing features are very convenient. However, they can introduce what I would call questionable quality elements into your mesh. Now, we'll get into a bigger discussion about this in class. But these lower quality elements are usually not a problem if they're away from where you are interested in calculating your stresses at. So we want to make sure we have nice looking elements at the edge of our hole. Away from it, maybe we don't care so much. Alright, so what we need to do next is what's called seeding the part instance. Okay, so dependent part instances cannot be edited or assigned mesh attributes. Try the operation on the associated part or select make independent from the instance in the model tree. That just sounds like a mess. What that means is this isn't where we want to mesh. What we want to do is we're going to go back to the part and mesh the part. Okay. So I'm going to switch this over to part, plate with a hole. And now I'm going to do this reseeding. And here it says a sizing control. They have a curvature control. That helps you get a good quality mesh. And let's see what this thing looks like with a global size of 10. So that means that approximately we're going to have 10 millimeter square elements, wherever I can put squares. Let's do this, apply. So you see these white things that showed up along the edge. That's basically going to be where our elements are going to be. All right, now we're going to mesh the part. It's going to ask us to confirm, and there it is. Okay, so it's got some nice square elements. The more square your element is, the better things usually work out numerically. You can see this element right here, that looks fairly trapezoidal shape, and this one right here, that's not a great looking element. It must have passed the kind of internal quality checks. But the thing that concerns me the most right now is it only has 3 elements here representing the curvature of that hole. I'd say that's not a very good mesh. I think we can do better than that, just even to start out with. So we're going to reseed it, and let's do a size of, I'm just going to say 4. Now it's going to pop up this warning. Do we want to delete this mesh, or do we want to make a new mesh on top of it? You really want to delete this mesh, so you may want to do this automatic deletion. But I'm going to select delete mesh. Okay, got rid of it, and now I'm going to remesh this part and confirm. And there it is. Okay, so that looks a little nicer. It's maybe a little bit coarse still around here, but it certainly looks a lot nicer than that 10 millimeter size. And hopefully this is few enough elements that we can run it even in the student edition. You probably won't be able to do your convergence analysis in the student edition. I still see some kind of questionable looking elements, maybe this one right here, maybe that one right there. Those angles, when they get kind of big like that, it gets kind of questionable, but generally it's okay. But so for our purposes, this mesh is going to be adequate. Now I want everybody to do this size mesh for this particular geometry component, and then I want you to pick another size mesh and repeat the process. And in both cases we're going to calculate the stress concentration factor. Let's go ahead and finish this off. So we're in the mesh, we're ready to get to creating a job and submitting it. So we're going to come down here, we're going to right click and create job 1 with model 1, that's fine. We're going to take all the defaults. The job is created but it's not submitted, so we have to right click and submit. And it shouldn't take too long. It's been submitted for analysis. It's running. If we want to monitor it, we can, and it's completed. Alright, now that it's completed, we're going to right click and go to results. It'll load in the results file. If we want to see the stresses, we're going to do this one, the contour on the deformed shape. If we want to make sure that it's behaving the way that we think it should, then we're going to animate it, and let's animate it with this one on the left, and it's going kind of fast, so let's slow that down. And it appears to be behaving the way that we think it should be. You see on the right edge it's kind of drawing inward, it's just pull and tension, and this is sliding straight up. It's not pulling away from that line of symmetry, so it's good. Let's advance to the last frame, and this is on the von Mises stress. We're going to change it to the stress in the vertical direction, the S22 stress, and the highest value looks like 2.117. So let's just check at the node. We're going to go Tools, Query, Node, Probe Values. Change this to the node. And the place with the highest stress should be this point right here. Okay, and it's 2.117. So how to interpret this number now? Okay, let's go back to our screen. We applied 0.8 megapascals on the top surface, which corresponds to 1 megapascal nominal stress. And so the stress concentration factor, let me put this in a different color, is defined as your maximum stress divided by our nominal stress. We have 1 over here, and let's go back and find out what that was. 2.117, let's call it 2.117, that's fine. It may be a little bit more accurate than we should have, but that's alright. So our stress concentration factor in this case is 2.117. Now if you do not put in the 0.8 megapascals or whatever it needs to be, if you change the different hole dimension, then you need to be a lot more careful about how you interpret that number to get the right stress concentration value. But now this is interesting. We have 2.117. That's not even right here. So we're not anywhere near this line. Well, the reason why is we have too coarse of a mesh, and another thing we could do is use what we call second order elements, but we'll learn about that more later. What I would like for you to try is, instead of using a element size of 4, maybe try an element size of 2 or an element size of 1. That will make the mesh a lot finer everywhere. Okay. So I want you to do what I did with element size of 4, but I want you to try a couple other element sizes. And I want you to send me your results in part of your homework for the stress concentration factor as you increase the number of elements. Now, if we had enough elements, we should see this dot right here, this green dot, start approaching this line as we have more and more elements. I think what you will find is it's going to take a lot of elements to get pretty close to 2.5 for a stress concentration factor. There are some other things we can do. Our third homework set, what I plan to do is talk about higher order elements and an optimized mesh so that we can approach our converged value for our stress concentration factor. Alright, so I think that's enough for this second homework problem. We will talk about this in a little bit more detail in class as well.